going to do on classifiers and supervised learning. So if we write on a schematic view of our data, so this is for supervised learning when we know the labels. In a couple of hours, we're going to move on to unsupervised learning when we don't know the labels. So let's finish that part on supervised learning. So that's what we've seen so far. Nearest mean classifier, linear discriminant classifier, rule-based classifiers, k-nearest neighbors classifiers. So today we're going to look at these ones. So decision tree classifiers, supervector machine classifiers, and classifier ensembles, and various techniques within that group. So let's consider this example. So this is we're going to look at a decision tree classifier. So, well, first of all, could we use a linear classifier here? And if not, or if yes, why? So what you have to do for the assignment is, you remember, pick up 2 points and try to find the line equation from that, and then with the sign on the data you have the class. Okay. If you had to pick up a line here, or 2 points to create a line, do you think it's going to work? Is it a good idea? No. Why not? The problem we got today on that dataset is that you see the blue points here, like splitting the red region in 2 parts. Well, if we had to take a line, I guess we put it somewhere along here maybe to split the 2 classes. But look, we got 4 blue points here, and if you had a line here, we'll have like 5 blue points here. So it's not going to work basically. So we need something slightly more complex. So what we've done so far is not really going to work on that type of data. So let's try to make maybe some kind of a rule-based classifier. So if x2 is greater than 4.5, which is here, we could say maybe that's class red. Well, we still have the same problem with the linear classifier. But at least we're able to separate the blues here from the red. So far with what we know, we could already do that. So really, what we want is to be able to separate this subgroup here from the rest. So if it's less, then this is blue. If it's above, well, we could split again. If x1 greater than 4.5, no, well then this is red. So if it's smaller, if x1 is smaller, then this is red. So we are on that side. We could do that split again. If x1 is greater than 6.5, then yes, this is red. No, this is blue. And when you have something that looks like this, in computer science, how do we call this type of structure? A tree. And to be more precise, it's a binary tree. Yes, no, yes, no. I mean, no, yes, no, yes, no, yes. So the decision tree classifier is going to build that type of tree. And now we'll be able to classify new objects. So these are the terminal nodes or leaves. Here are intermediate nodes. And here at the top, this is our root. So I've applied two classifiers here. One is a one nearest neighbor, one is a decision tree. So which one is which?
Decision tree is this. The nearest neighbor is this.
Decision tree on the right hand side,
Nearest neighbor.
nearest neighbors on the left hand side. Yes. And you can clearly see here the split. That's like straight. Right. So the next class of, the next type of classifier is a support vector machine classifier. So you have data in the original space, like when we give you that spreadsheet. We transform it. It could be in a higher dimension, for example. So we take the data and somehow we transform it. So what we're trying to do is to build a linear classifier in that new space. Then, when we have this, we can go back to the original space and classify in and get the data in the result in the original space. So what this type of classifier is doing is apply a transformation on this. Then run a classifier on this transformed data using a linear classifier. So this is a kernel trick, and there are various ways to do that transformation, and this is something you can usually configure in the packages that you use. Like I heard people asking me about scikit-learn this morning, so things like that. So the training of our classifier is transforming the data in that new space, training the linear classifier on the data in that new space, and then the back transformation. So the super vector machine classifier is called a large margin classifier. So here you can see like we have our line here, our linear classifier here, and you can see the distance of that point, the point the nearest to the line, from the red point and the blue point, and the distance here is the same, right? If we transform in a new space, we try to maximize the space here and here. So we want to maximize the separation between the two classes. So you can see that the space has been transformed on this plot. This is the same data, but somehow transformed. So that's a small margin, you can see it's quite small. And here this is a large margin. So the support vector classifier is a large margin classifier. So these points here, they are called the super vectors. That's from the name. So these are the points that we're going to use to transform the data. And you can see that when we have our linear classifier and put it back in the original space, now we no longer have linear boundaries until slide 12 of these lectures. We will have drawn lines. Now you can see we could have curves. And obviously we can do more complex classification with this type of classifier, which is why they are quite popular. And on this example, you can see the boundary here. There's no way we could have done that with our decision tree, or I mean decision tree maybe, but or rule-based classifiers. That would have been far too complex to do. The next type of classifier, which is the last one that we're going to touch in these lectures, this is called classifier ensembles. So far, we had one classifier, a set of features, and then we assign a class label. Well, now, we've seen different types of classifiers. SVM, decision tree, linear classifiers. Well, the idea is that maybe we could train more than one classifier, different classifiers, and somehow combine their results together. So for ensembles, you have more than one classifier. And you can select which one you want to include in a classifier ensemble. The question is, how do you combine the results? What do you think we could do? So we got maybe one classifier, another one, and we stop at 3. So that's the same data, and then we have a prediction. Maybe it says this is class 2. And that says this is class 2. And maybe this one says this is class 1. Somehow we need to combine these results into something. What do you think the class should be? 2? No. Let's consider you're talking to a computer. Computers are very stupid, you know. You have to tell them exactly what they need to do. How do you know this is 2? This is probably right, but how do you know?
Looking at the majority predictions, I think.
So, yes, that's the majority. The majority of the classifiers said it was 2, so maybe we should consider that this is 2. So, it's like there is a vote, and whoever wins most of the vote wins. So that's one way to combine these results. You're right. So another way of doing it, it's maybe select only one answer. So there are various strategies to do that, and we are going to see a few. So we could fuse the results, so that's classifier fusion, we use them all. Or we only pick one. So this is classifier selection. So there are 2 strategies, fusion and selection. We could build an intermediate feature space, and then we could use any. So several strategies I said. One is called bagging, and we take L independent bootstrap samples of the dataset. So remember our lecture 2 on datasets. So the dataset is called Z, capital Z. Bootstrap, I'll show you a visual example of bootstrap. So we have our training data. Remember. So we're given a dataset, and we need one part for training, one part for testing. Remember building the confusion matrix? So we need to be able to do that, and we've seen various strategies to split the data into two. So Bootstrap, what is it? Forget about the web. We are in machine learning. Good try. So in this context, Bootstrap, well, we're going to build a training set. And we're going to pick random points, random objects in that set to build something for training. And what happens in Bootstrap is purely random. So we just take random samples here, and an object could be repeated several times. So we take L. So L, if I go back, no, it's not returning. L is the number of classifier. So then, for a given object X, we each classifier is, so we train a classifier on each sample. So for now, so we consider every classifier has been trained. For a given object X, we calculate the class label from the L classifiers. So now we've trained that on one Bootstrap sample, on one Bootstrap sample, on one Bootstrap sample. So they're trained. We got another object X here, and we have these predictions. And then we apply the majority vote to combine the ensemble votes. So just like what you explained earlier. So we got our L samples, Bootstrap samples. We train the different classifiers, so every classifier on a different sample. Now we do a prediction on X. We have L labels, and we have the majority vote. And that's going to be the final label for X. So here's an example. It's what I try to do here. So now we got X, the different classifiers, class 3, 1, 3, 2, majority, well, here in that case, this is 3. So a different strategy to sample or dataset Z is a subsample. So in subsample, it's without replacement. So consider this is our dataset, right? And we're going to pick up rows from that dataset, random rows. So this is what we get. The thing here, an object cannot be repeated twice. That's the thing. It can't be repeated twice. Whereas I said we could for Bootstrap. And when we sort, you can clearly see here that we haven't repeated the objects. When I do the same for bootstrapping, you can see that we can repeat. You can see here. There is we have the right to repeat. So that the two different strategies here. Right, so for boosting, it's a slightly different approach. So we take L-dependent bootstrap samples. Each subsequent sample should contain larger proportion of objects misclassified by the ensemble up to that point. We train a classifier on each sample. For a given object X, calculate the class label from the L classifiers, and then we apply a weighted majority vote to combine the ensembles. So in boosting, we have the notion of weight. No weight here. Now we have weights. So let's see a visual example again, but in that case. So we got our L samples, we got our L classifiers, we trained them, now we can make a prediction. So we have L predictions, and then see what we introduce here, a weight. And the sum of the weight is 1. So random subspace, so a different approach, so we take L independent subsamples of the feature set. So bootstrap samples, subsample in that case. We train a classifier on each feature subspace. For a given object X, we calculate the class label with the L classifiers. Then we apply a majority vote to combine the vote and again. So similar things. L samples, L classifiers, a new object that we want to classify. We have L labels, and then we do our majority vote. So the difference here from the first one we've seen is that the way we create the samples. So the last one we're going to see is called random forest. So we take L independent bootstrap samples of the dataset Z. We train a random tree classifier on each sample. So that's the type of classifier we've seen before. We get a new object we want to classify, we got the label, and then we apply a single majority vote. So our samples or decision tree classifiers. In that case, this is fixed. This is the type of classifier we have to use. Or object we want to classify. We have L labels, and then we got our majority vote. So what's going to vary between these different strategies? Well, how do we sample our original dataset? Is it bootstrap? Is it subsample? And also what type of classifier we are going to use. So for random forest, it has to be a decision tree classifier. So usually classifier ensembles work better than a single classifier. And can anyone guess what is the underlying reason for that?
I think because it's getting more data input, so it's comparing from different classifiers, or for instance the random forest is checking so many decision trees, so not just one, and it's comparing them and picking out the best, so you would get a higher prediction.
Yeah, that's totally true what you're saying. So if we were to make an analogy, like we're stronger together, have you heard that phrase? So the idea is that maybe a weak classifier on its own, well, it's weak. It's not going to be good. But when you take two weak classifiers and combine them together, they might become stronger. Yes?
So can it be described based on errors, like reduction of errors?
Well, yes, that's the point, yes. So by combining more than one classifier, we can build a strongest classifier. So if that's the classification region that we desire, and we have these nine classification region, well, we could try to combine them together. So these are being generated by 9 different classifiers. And when we put things together, this is what we get. Don't you say that 9 weak classifiers are stronger when they're put together? I'm sure we all agree that the picture on the right hand side is a lot closer to that one than any. These ones are not as good as this one, right? So usually, I don't say always, but usually, classifier ensembles work better than single classifiers. So something you could try in your own time is to design by hand a decision tree classifier for that data. Or maybe we'll do it. Maybe we'll do it. We have a bit of time. So that one question that we can answer now. And another question here, and I put the answers at the end of the slideshow. So you have this dataset, and I mean you have the classifiers here, and their rules for the different classes, and you can see they all differ. And how to build the classifier ensembles from this. So let's say we do that together. So we need to start somewhere. Where are we going to put the root here? X1 X1 less than
0.
No, not 0. X1 is here. So if we put it at here, like we're not really going to. Can anyone have another guess?
X1 greater than 2. That's for the.
Greater. Well, I'll put smaller, but you can put greater. Greater than 2.
Yeah.
So that's our root.
That's for the.
No.
Circle.
Yes. So what are you suggesting? So if it's greater than 2, then this is class blue. And here, well, we need to do more tests then. So now this side is sorted, and we need to split the space so that we can separate the yellows from the green. So what's your next test?
X2
X2. Oh, I want to keep the same convention. You said greater than before. We keep greater than. Minus 2. No. Yes. Okay, so if it's greater than minus 2,
Green.
yellow. Else, green. So if it's smaller, this is green. Yes.
I'm sorry, when it's no, what's the value of x2?
Sorry?
When it's no, what's the value? What are the possible values of x2?
When it's
x2
no.
greater than minus 2. What are the possible values?
Yeah. If x2 is, I don't know, if x2 is equal to 1, then this is 0. So, which is true, if it's here. You want to separate the space in binaries in two parts. I decided it'd be greater than because I was teasing you. I like things to be in order and follow the same convention. And like, you know, if you follow one rule in an assignment or in your dissertation, like, you should often like stick to that rule. We could have done another classifier. We could have done x1 smaller than 2. That would have been fine as well. And we could have had x2 smaller than minus 2. We could have done that as well. Or any possible combination. I don't really want to start this because I don't think we have the time to finish it. Well, I guess maybe we can start. I don't know. It's a lot of computation, so that's something for you to do at home. But basically, what you will need to do, so you have the different classifiers, there are different discriminant functions here. You got a new input x equals to 3, so you have to replace x with 3 in all these equations, and then look for the sign, and you can see here the answers. So basically here 3 minus 2, this is 1. Well, this is 3. This is 4. 5 minus 3, this is 2. 3 plus 1, this is 4. And you do it for all the discriminant functions. So this is minus 1. 3 plus 2, this is 5. Minus 3. 3 times 3 minus 10, this is 9 minus 10, this is minus 1. 4 times 3 minus 20, this is 12 minus 20, this is minus 8, etc., etc., etc. And then we look for the largest Are you just arriving for my lecture? You know we finished already. I can't mark you present. So then we look at the largest value. So 1, 5, 4, 4, 4 here. So this is class 1. So classifier 1 classifies this input as class 1. Classifier 2 classifies this input as class 2. Class 1, class 3, class 1. Majority vote. How many class 1? 1, 2, 3. How many class 2? 1. How many class 3? 1. Majority vote? Well, that'll be class 1. And you know, these questions, I already said it, but they are good practice for you to do at home, because that's the kind of thing you might expect in an exam. Hint, hint.
That's alright. I don't understand. Everything on the class 1 is positive.
Well, I mean,
All classifier.
no, I mean on this one is because there are more than you are looking at the largest value. So classifier 1 has 3 functions here. So you replace the x's with 3. So 3 minus 2, this is 1. Minus 1. 3 times 3 I mean minus 3 times 3 plus 4, this is minus 9 plus 4, this is minus 5. What is the largest value? 1. And what is the corresponding class? Class 1. Which is it?
Is the classifier 1 and class 1 is this minus 13 minus 5 instead of 13? 13 instead of minus 5.
13. I don't see a 13.
If you do minus x square, it's become 9, not minus 4.
Which classifier?
Minus x square plus 4.
Classifier 1, class 3.
Yeah.
If I do the math, it's 9 plus 4.
No. You are doing that one. So this is not the same. So if you want, we could have written it like this. So that's what we meant. So I see what you mean. Okay, so we start here for now. There is no time to start another lecture or exercise. But when we get back together again at 3, I believe, we won't consider that we got the class labels. We want to guess them. So this is the difference between supervised learning and unsupervised learning. Classifiers, this is what we've seen so far. And now I'm going to talk about clustering. So see you at 3.